All right, in this video, we are going to talk about some organometallic reactions, some organometallic chemistry. Specifically, we're going to be looking at some coupling reactions catalyzed by metals. So there's four reactions we're really going to look at. The first is the Stille reaction. I guess I have the same thing written twice here. So in here, what we're going to be doing is taking a organo-tin complex, coupling that with a alkyl or aryl halide. That's coupled with a palladium metal and a ligand set to get the coupled product of R1 and R2. All right, so our main product is really coupling these two carbons, right? One is attached to a tin, the other is attached to a halide. All right, so typically R1 and R2 are sp2 hybridized carbons. All right, so these carbons are going to be sp2 hybridized. So they really can be vinyl, right, or aryl halides in tin. I also want to remind you that we can use pseudo halides, so like a triflate group works really well to do this reaction. All right, and we'll show an example of that in a second. So if you take your vinyl halide here, and iodine is going to react with bromine, couple it with your tin complex, okay, and then you use a palladium catalyst, In our test, we can just write palladium catalyst because there's a lot of different palladium catalysts we can see. We can see we formed our new bond here, our new carbon-carbon bond has been formed. Another example here is we have our vinyl halide, our tin complex here. Again, the sp2 carbon is going to be coupled, right? So if we put a dot here and a dot there, right, that is our new bond that is formed. And again, we have a palladium catalyst that is catalyzing this reaction. So we're using a palladium catalyst. This is catalytic. There's an interesting catalytic cycle for these metal coupling reactions. So we start with palladium 0 that will add in a process called oxidative addition in between your carbon-halogen bond, forming this complex here. So the metal has been oxidized. That's why it's called oxidative addition. Then you have a process called transmetallation, right, where the tin carbon complex will switch. So the halogen will then be bound to the tin, right, and R2 will then be bound to the palladium. That's called transmetallation. And then finally, we have a process called reductive elimination, where your metal goes back to palladium 0 and you formed your coupled product. So these are just some of the words to kind of describe what's going on here. I want to just show you sort of an interesting example. Let's say you have a ketone. We can use LDA followed by triflate anhydride to form this complex here. And that's a great way to do a coupling reaction. Again, this is a pseudo halide. So you can now treat this with a palladium catalyst and then some tin derivative to get your new complex here. So we've done our Stille coupling here by adding this alkene to this position here. All right, so this is just showing you how we can use our triflate from a ketone to do the Stille coupling. All right, next reaction I want to talk about is the Heck reaction. Again, very similar, but you don't need an extra metal. So you have R and R prime, R and R prime, all right? And you're now going to couple these two together. Okay, so essentially our R group, right, is coupled to the end of the alkene. And again, that's done using a palladium catalyst. And we can just write palladium catalyst because there's a lot of them. So an example here is we take our aromatic ring with our bromine. We have our alkene at the end, and then those two carbons are coupled via palladium. That's called the Heck reaction. This has a different catalytic cycle. It's catalytic in palladium. I'm not going to ask you about this, this cycle here, but you really start with like a palladium 0 complex that will insert into your carbon-bromine bond here to get carbon 2. Your alkene will then associate with the palladium complex, and then it will bind, the palladium will bind to your carbon atom, right? Then it abstracts a hydrogen, so the alkene is now associated with it, and that falls off to get your final product. That's really the catalytic cycle you see for the Heck reaction. So here's another example here. We have iodobenzene. We have our alkene. Right, the alkene is now coupled to the complex there via the Heck reaction. Right, and again, we can just write palladium cat to get that done. All right, the third reaction we want to talk about is the Suzuki coupling, or the Suzuki reaction, very similar to the Stille, okay? But instead of using tin, we're going to be using boron. We're going to be using boron. Okay, so very, very similar. Again, R1 and R2 are sp2 hybridized carbons. And again, you simply couple these using a palladium catalyst. And typically in this reaction, you need to use a base, and then we get our coupled product. Here's the catalytic cycle. Okay, very similar to the Stille. Oxidative addition inserts the palladium in between R2 and your halogen or pseudohalide. Okay, usually you use a base because that will replace the halogen. Transmetallation with your boron complex, right, results in R2 and R1 connected to the palladium, and then reductive elimination gets out your product. All right, so let's look at an example here. Let's kind of ignore how this is made. It's a lot easier to make these boronate esters. So this is a boronate ester from an alkyne. So let me just show you that reaction. Right, so if you just take a terminal alkyne, this is just like the hydroboration reaction. So you can simply treat it with some HBr2, and that will add the boron to the anti-Markarnikov position. Oops, sorry, I didn't write that right. Let's erase Br2. So typically things you can use are like catechol borane, that's a good boron complex to use, or this. Those are really good borenes to use to get your compound here, right? And we're just doing basically a hydroboration of an alkyne. That gets your boronate. You then add your vinyl halide, and our palladium catalyst, right? And then you're able to get those two compounds coupled. Let's put the dots in red. So there's our carbon in red, there's our carbon in blue, and this is the final product that is formed. All right, so the easiest way to make these boronate esters is really from an alkyne, using one of these two compounds. Now there's a lot of different boronic acids and boronic esters that people use. There's hundreds and hundreds of them, so these are two of the most common. But really we're focusing on sort of the coupling aspect of that, right? This is called the Suzuki reaction, very similar to the Stille reaction. And here's just sort of another example kind of showing that here. The last metal reaction is a little different. It's not a coupling reaction. It's called a metathesis. This original work started using molybdenum, but now everybody uses these ruthenium catalysts. So a scientist by the name of Grubb really developed these. So these are Grubb's ruthenium catalysts, and he has a couple different versions of those. Again, when we're using this reagent, we can just write RuCat. All right. There's different types of metathesis processes. There's cross metatheses when you're mixing two different compounds together, ring opening, ring closing metathesis, and then ring opening polymerization. So here's the polymerization process here. We're really going to be focusing on the ring closing metathesis. That's really the most common way this is used. So we'll be focusing on ring closing metathesis, RCM. All right. And in this compound here, you're coupling two alkenes together, right? But you lose those carbons. You lose those carbons. So you're losing two carbons in this reaction. So it's pretty simple, right? You have two alkenes, all right? You just simply add your catalyst. We can just write RuCat, right? There's the specific catalyst that's used, RuCat. And you see those are now coupled together to form an alkene, right? And you've lost these two carbons at the end. You've lost those two carbons at the end. So if we number here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's your ring closing metathesis. And what's great about this reaction, it works really, really well, right? So it works well, and it works on really big chains. So if the chains are really long, you're able to form really large rings. That's what makes it really useful. All right, so we'll be focusing really more on the ring closing metathesis. Here's an example of the cross metathesis. When you have two different alkenes, right? You have the carbons in the middle. You've got your red carbons that you're going to lose, right? So your compound now is just the two blue carbons connected together. This has a really interesting catalytic cycle here. So if you take a look at it, the metal basically inserts via a 2+2 reaction. To get you this four-membered ring here. That happens again, where you lose two carbons. So now you have your metal connected to the internal carbon here. That happens again, right? So if we kind of think about these connecting, those double bonds move to get, again, our four-membered ring. And then the electrons again move, so you again lose a carbon in your metal, and you now get your coupled compound with just the internal alkenes. So the Sonegashira coupling, we're just going to kind of ignore that. We don't really need to worry about that one. That's just another example, but we don't need to really worry about that reaction too much. All right, so I just want to show you an application. There's a paper here, right? They were working on the total synthesis of a couple specific compounds. All right, so they're trying to synthesize kind of this class of compounds here. You see you have a large ring that they want to make, and they're investigating a few reactions. The catalysts they're using are the Grubbs catalysts. They tried 2 different types of those catalysts here, right? The key to focus is on is they have the ruthenium catalyst as well. So let's look at the basic setup, or the basic sequence here. So in A, right, step A here, they're actually making an ester. They're making an ester. So we're used to learning that we could do something like this using the Fischer esterification, right? But it turns out the Fischer esterification is not really good when you have sort of these long chains. It just doesn't, the reaction doesn't really work that well. So they used a different reaction called the Mitsunobu reaction. The Mitsunobu reaction. So in the Mitsunobu reaction, you take a carboxylic acid and you take an alcohol. And then the reagents you need are triphenylphosphine and DEAD. Let me give you the structure of DEAD. That's diethyl dicarboxylate. Right, so that is diethyl dicarboxylate. It's an ester connected to 2 ends and another ester at the end. That's DEAD. And in this reaction, you can basically see you basically have formed your ester here. And if there's ever stereochemistry on the alcohol part, that gets inverted. So there's a really interesting mechanism here. The triphenylphosphine attacks the nitrogen. The nitrogen deprotonates the carboxylic acid. Okay, the carboxylic acid, to form this sequence here. All right. Your alcohol basically attacks the triphenylphosphine. So the alcohol is served as basically you've now formed a good leaving group. And then your carboxylic acid attacks the O, kicking out the phosphine. And that's why you get the inversion of stereochemistry at the alcohol. The O from the carboxylic acid is actually the O that's found here. And that's different than the Fischer esterification. All right, that's called the Mitsunobu reaction. So if we go back to how they used the Mitsunobu reaction, they added triphenylphosphine, DEAD, and then they added the alcohol, 9 decenol, so that is an alcohol, 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9. Double bond here. So when they add that alcohol here, right, with triphenylphosphine and DEAD, you get the ester. And then they're really looking at now coupling these 2 alkenes together, right? Coupling these 2 alkenes together. So in step B, again, they utilize complex 5, right? That's over here. That is our RU catalyst. That's our Grubbs catalyst. And again, what you'll see here is the internal carbons are the carbons that are connected. So those 2 carbons are connected in blue. So we kind of number these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've got carbon 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Right, so our connection is from carbon 2 to carbon 15. Right, and this is really showing you that you can form really large rings using the ring closing metathesis reaction. All right, generally you're going to get E over Z, so generally speaking you're getting ratios of E over Z, so you'll normally be forming the E alkene. And I just want to show one more scheme here, all right, to kind of put all this together. So they start with compound 9, right? We've got a phenol functional group. So in A, they first do the Mitsunobu reaction. They add 9-decenol. We've already seen that structure, triphenylphosphine and DAD. So that's the Mitsunobu reaction, right? That adds on this carbon chain here. In step B, right, next is step B, they're converting OH to O-triflate. That's going to be our pseudo-halide. So they can do the metal coupling reaction. So step B, they're just treating this with triflate anhydride and pyridine. Triflate anhydride and pyridine. So that converts this to the O-triflate, right? R is our triflate here. That allows the researchers now to add in the alkene functional group here. This is the Stille coupling. So they're using tributyl tin vinyl chloride, right? Tributyl vinyl staining, they call it, but that's tributyl group tin with the alkene. Oops, sorry, I drew that wrong. So that will now couple this carbon in blue to that carbon in blue, giving you the alkene functional group. So that is our Stille reaction. And then again, remember, we need a palladium catalyst to complete that. That gives compound 12, which is perfectly set up to do the ring closing metathesis reaction, right? So they use the Ru catalyst that will couple the inside alkene to the inside alkene here. Those are now coupled by generally a trans alkene. And then you can see they've repeated this a couple different ways that look at synthesizing other compounds, but really I just wanted to highlight scheme 2. Again, to recap, Mitsunobu reaction to form the ester. Sorry, I think I might have mistaken this first. Mitsunobu reaction to form the ester. Okay. Then they, that's step A. Step B, right? Step B, they converted the phenol into our triflate. That's step B. Step 3, we'll do in green, they did the Stille. Okay, the Stille in step 3 converts this O-triflate into the alkene. And then they finally used the ruthenium catalyst to couple these two reagents together. All right, so that's just a summary of a few organometallic reactions for us to review: the Stille reaction, Heck reaction, Suzuki reaction, and olefin metathesis, and then just a paper kind of describing how this was done.